Welcome to The Explainer. Today, we're diving into the ultimate neurological whodunit. We're looking at the mystery of infantile amnesia and trying to figure out why your earliest years are just a complete blank slate. It's kind of a crazy paradox, right? We literally learn more in our first 3 years of life than at almost any other time. How to walk, how to talk, how to interact with the world around us. And yet, if you try to pull up a memory from those foundational moments, nothing. Just a void. Today we're going to decode exactly why it is probably for the best that you can't remember being a baby.
Okay, let's kick off this investigation with a quick test. I want you to search your own brain right now. Think about your absolute earliest memory. Do you have it? Awesome. Now, how old do you think you were when that event actually happened? Lock that number in because the data suggests you are almost certainly wrong. And here is why. A massive 21-year study out of Memorial University found something really fascinating. The average age of our earliest memory is actually 2.5 years old. That's a full year earlier than experts previously believed. By interviewing hundreds of people and cross-referencing their memories with their parents' accounts, researchers prove that you actually remember much further back than you think you do.
This brilliantly illustrates why you probably just misdated your own memory a second ago. It comes down to a mental trick called telescoping. When we look back at remote memories, it's kind of like looking through a camera lens that pulls distant objects closer to you. This telescoping effect shifts our earliest memories forward in our minds, tricking us into believing we were, say, 3 or 4, when we were actually only 2.5. But hey, even with that adjusted timeline, the entire first 2 years of your life are still just missing in action.
So let's get into part 1, the hardware. We're investigating the growing grain.
To find out where those early memories went, we have to start by interrogating the physical suspects. Let's look at the hardware inside your rapidly growing infant skull. In our first 2 years, our brain size absolutely explodes. We're talking going from just 25% of adult size at birth to a whopping 75% by age 2. And during that massive growth spurt, a region deep inside the hippocampus, which is your brain's memory center, called the dentate gyrus, goes into absolute overdrive. It's pumping out massive amounts of brand new neurons in a process called neurogenesis.
You can actually see this happening in these fluorescent maps from a neurological study. On the left, we've got the hippocampus of an infant mouse. See all that intense bright green webbing? Those are massive numbers of freshly generated neurons growing and projecting connections. Now, compare that to the adult mouse on the right. The growth has drastically slowed down. That explosive, bright green neurogenesis in the infant brain, that's a prime suspect in our memory mystery.
Here's the deal. Our brains are constantly balancing this ultimate trade-off between plasticity and stability. Plasticity is our ability to absorb new information, and stability is the ability to actually hang on to those established memories without them degrading over time. Because the infant hippocampus is churning out so many new neurons to learn about the world, those new neurons are aggressively wiring themselves into existing circuits. And as they integrate, they literally overwrite, disrupt, and degrade the early memories that were just stored there.
We can actually prove this hardware theory by looking at the animal kingdom. Infant mice are born with immature brains that go through rapid postnatal growth. And just like humans, this scrambles their memory circuits and causes them to forget things quickly. But what about precocial animals like guinea pigs and dagas? They have much longer gestation periods and are born with highly mature brains. Because they completely skip that massive postnatal surge in new neurons, get this, they don't experience infantile amnesia at all. Their early memories remain totally stable.
All right, let's move to part 2, the hardware, pruning the synapses.
Because it's not just the creation of new neurons causing amnesia, there's also a biological shredder inside your head known as synaptic pruning. Think of synaptic pruning just like trimming a rose bush. By cutting away the extra, unnecessary stems and leaves, the main plant can thrive and grow stronger. This is your brain's version of spring cleaning. In early childhood, your brain creates way more connections than it could ever need. So to become efficient and organized, it has to systematically clear out the unused early pathways to make room for better, faster processing.
Let's walk through how this works. First, the infant brain overproduces connections. Then, through a strict use it or lose it rule, repeated experiences strengthen the pathways that actually matter. By step 3, any unused connections, which might contain early, fleeting memories, are flagged as weak. Finally, special immune-like cells called microglia act like microscopic trash collectors. They swoop in and systematically dismantle those unneeded pathways. If a memory was living in a connection that wasn't reinforced, it just gets swept away.
Now for part 3, the software, language and the sense of self.
We've looked at the hardware, but now we've got to interrogate the psychological software. Specifically, how infant minds just lack the early tools to save memories properly in the first place. The biggest software update our brain ever gets is language. Language acts as this critical organizational scaffold. Studies show that if an event happens to you before you have the vocabulary to describe it, you simply cannot translate that nonverbal, sensory memory into a verbal story later in life. You didn't have the linguistic folders to file the memory away properly, so your older verbal brain just has no way to open the file.
On top of that, an autobiographical memory requires a you to actually remember it. You can't have a memory about yourself if you don't know who you are yet. As this timeline shows, our cohesive, narrative sense of self takes over 2 full years to gradually boot up. We start out as just a sensory self, purely taking in physical data. It takes until around 24 months to develop a verbal self. To have a real episodic memory of your life, you need that continuous self-narrative to hook the memory onto.
This is beautifully demonstrated by something called the delayed self-video test. Researchers sneakily put a sticker on a child's head while recording them, and then show them the video a few minutes later. A 3-year-old will point at the screen and say, "Hey, that's me with a sticker," but they don't do anything else. But by age 4, a child will watch the video and immediately reach up to their own head to pull the sticker off. It isn't until around age 4 that children develop a temporal sense of self. The realization that the past you on the screen is the exact same continuous entity as the present you sitting in the chair. Without that temporal self, early memories simply don't stick.
Which brings us to part 4, the verdict. Are early memories truly lost?
So, we've got rapid neurogenesis rewriting the circuits, intense synaptic pruning shredding the pathways, and the slow boot up of language and self-awareness. What's the final verdict here? Are these missing memories gone forever? Interestingly, babies absolutely do form long-term memories. Studies show that 3-year-olds can actually recall specific events from when they were just 1 year old, like meeting a stranger. But because of the extreme immaturity of their memory processes and all that brain remodeling we just talked about, a phenomenon known as childhood amnesia wipes the slate clean by the time they hit age 7. The memories form, but then they fade away.
But hold on, because groundbreaking new fMRI scans from Yale are challenging everything we thought we knew. By scanning the brains of awake infants, researchers discovered that babies' hippocampi are highly active and are, in fact, successfully encoding specific, episodic memories deep in the posterior part of the brain. The infant brain is doing the work. The data is being recorded.
Which leaves us with this final, lingering mystery. If the infant brain successfully recorded the data, did the hardware updates, the new neurons, and the pruning actually delete it? Or is this purely a software issue, where our adult, language-based brains are just completely unable to open the old, pre-verbal files? It turns out infantile amnesia might primarily be a retrieval problem.
I'm going to leave you with this profound thought from Nick Turk-Brown and his research team at Yale. They're actively entertaining the radical, almost sci-fi possibility that every single moment of your infancy, every hug, every new texture you discovered, might still endure in some locked-away form inside your adult brain. The memories might not be dead. They might just be waiting in the dark for a key we haven't found yet. Thanks so much for joining me on this explainer, and I will catch you in the next one.